Okay, so we're going to get into polar form and we're going to look at this kind of new way of writing our complex numbers. So the word or the name, I suppose, that we've given to the way that we were writing our complex numbers, which is this a plus bi here. So we call that Cartesian form or rectangular form. That's kind of the name that we give to that format, the a plus bi. That a and b then represents like our position on the complex plane. So we saw that with the Argand diagrams. Um, with the A kind of representing where we're going on the real axis, the B part representing where I'm going on the imaginary axis. So we have another way of looking at these complex numbers, and that's called polar form, which is a particular kind of, or makes reference, I suppose, to a particular type of coordinate, which is polar coordinates. And when we're writing a complex number in polar form, the format that we end up with is this format over here, where our complex number z is considered to be or multiplied by cos theta plus I sine theta. Now we have to just, of course, obviously consider what those letters and variables mean. So in terms of this complex number, the value for or is our modulus. And we should remember that the modulus of our complex number is square root of a squared plus b squared. Okay, so the modulus was the distance from the complex number to the origin, and we would have looked at that being the same as a squared plus b squared. Okay, it's kind of reference to our Pythagoras' theorem there. Theta then, the word for that we use for theta is, it's called the argument of the complex number. And we note here that theta is tan inverse of b over a. So theta is, if we consider, actually I shouldn't have wrote it out, if we consider this example that we have here, so say this is my complex number, this would be my modulus, and then this would be my argument here, this angle that it makes, with the positive real axis. And that's kind of convention, I suppose, if you like. It's kind of the way that we just tend to do things when we're talking about complex numbers. So we say that that angle is the angle it makes with the positive real axis. And generally that means that theta is going to be between pi and minus pi. So we're going to end up with having negative values for pi, which is fine. And we kind of should remember as well that a negative value of pi just means that we're going the opposite way from the from 0, 0 there, from kind of the start of our positive real axis. If we're going clockwise, which isn't the way we normally go kind of anti-clockwise. But if we go clockwise, we then consider that to be moving in the negative direction. So we would have seen before that if I was to take this same example here, say I just get rid of those two bits. So if I was to go to maybe this point here, we might say that maybe this is an angle of 60 degrees. So we could say that I've gone minus 60 degrees, or if I went the whole way around here, that I have gone 300 degrees. So either 300 degrees or minus 60 degrees, depending on the direction that we're considering that we're coming from, I suppose. So that's just important for us to remember. But generally, with our complex numbers in polar form, we are writing them with modulus or times cos theta plus I sine theta, where theta is called the argument of the complex number. And when we're writing a complex number in polar form, what I've said is we have to pay attention to the position of the number on the convex plane, as this will affect the argument. So if the number is above the real axis, then the argument will be positive. And this is just what I was saying there. So if it's above the real axis, that angle, we're going to take it as being a positive angle. So all the way around here, starting from that real axis, working my way the whole way around, that would give me an angle all the way from 0 up to pi. Now, if we're going under the axis, so below the real axis, we're going to be going down this way, and we're going to be considering the negative versions all the way up to, again, a negative pi, a negative version of pi. So we might end up with, if we consider, say, maybe halfway here, so this would be our kind of 90 degrees, or pi over 2, so that might be a version of minus pi over 2, to show that we've gone kind of that opposite way, the clockwise version. So just to note, I suppose that's important for you to remember. If the number is above the real axis, the argument's positive. If it's below the real axis, we're going to say the argument is negative. So we have a few steps then that we'll remember when we're converting to polar form. And again, we just kind of get into the habit of these steps, I suppose, and we just get used to kind of working with them. But our steps are to sketch the position of the complex number, to find the modulus, to then find what we'll call the reference angle, and we're going to call that one alpha. Just to keep it again, just to keep it consistent, to use the same letter all the time. And I've made a note here as well that we're taking tan of alpha as positive, and we'll see what that looks like when we look at one of the examples. We'll just consider what we mean exactly by that. And then when we find that, we're finding theta using the appropriate sign for your answer. So bearing in mind what we've looked at above here, that if theta is above the real axis, it's positive. If it's below the real axis, it's negative. I've just made a note as well here that if we're looking for complex numbers with only a real part or an imaginary part, then with our sketch, we can kind of already work out those angles. So like we looked at there already, if I go here and go kind of back 90 degrees or pi over 2, then that angle is going to be minus pi over 2. Okay, same thing goes then if I go the full way 180 degrees or pi. We can already kind of work out those without having to use reference angles or use anything like that. We can kind of see the value of theta just by eyeballing it, by looking at the question. We're going to look at these examples here now as per, I suppose, as per with all the notes we've done. These are the same examples that are in your notes, so you can kind of follow along or sketch along, kind of put in some annotations or whatever you like into your notes if you want. But let's just look at the first one. So we have 3 plus root 3i. So our steps were that first of all, we are going to sketch where our complex number is. And it very much just has to be a sketch. Really what we're trying to see is just which quadrant of my plane am I looking at? Which section of my plane am I in? And then in a way, this is very similar to when we would have done the trig equations. We're doing a lot of the same steps here, finding reference angles, finding things like that. So looking at the question here, my modulus is going to be this value here, and I'm going to sketch in my value alpha here. This is my reference angle that I have, and then we can include as well my value for theta here. And we'll make a note as well that theta is going to be positive because I'm above the real axis. So let's start maybe by finding my modulus. So that's the square root of a squared plus b squared. So the square root of 3 squared plus root 3 squared, which is 9 plus 3, which is going to be the square root of 12. Okay, square root of 12. And then if we continue with the next part of that one, then we're going to look for a value of alpha. So tan of alpha is going to be equal to b over a. And this was the part where I said we take those values to be positive. So what we're really doing when we're looking for our reference angles is we're considering the triangle that would have the same angle here and taking these values as being just positive values, and we're just trying to work out what would that angle be. So if we had, as we will have in the other examples, maybe negative values for that, we just are considering, you know, what happens then if I just take that whole value to be positive, because we can't really work with if we include negative values there, that just kind of throws off our calculations in the same way that it did when we did the trig equation once. So we want to consider that tan alpha part to be equal to just something positive, and we're going to find a nice angle for alpha that's between kind of 0 and 90, or 0 and pi over 2. And so let's just do that then by getting our tan inverse here. So let's have a look. So tan inverse of square root of 3 over 3. Let me just get that in right. So root 3 over 3, and we get pi over 6. Pi over 6. Pi over 6. Gorge. Okay. So we get a value for alpha of pi over 6. Now we haven't found the actual value of theta yet, but for this question, theta is going to be the same as alpha, and we don't need to change the sign, or we don't need to take it away from anything. It's just going to have the exact same value. So what that means for us is that for this first question, our complex number, remembering that the format we're writing it in is or cos theta plus I sine theta, we're going to get a value of root 12 cos pi over 6 plus I sine pi over 6. And that's our kind of answer for that first part there, I suppose. So we'll see, we might go through all of these examples, but let's just look maybe at the second one here, just so we can see another kind of option that we have for these ones. So again, we start by sketching it out. So the second one here, it's minus root 3 plus I. So if we consider it maybe to be around about here, and we're going to have my value of or here, I'm going to have my alpha. And for this one then, theta is going to be the whole way around here. And again, it's still going to be positive because we're still above the real axis. So we'll start by finding the value for my modulus. So minus root 3 squared plus 1 squared. So I get 3 plus 1, which is 4, which is a value of 2. Then if I'm starting to find my reference angle, and this is where I was saying we take these values to be positive, so it's b over a, so it's 1 over root 3, and then to get the value of alpha, I'm going to take the tan inverse of 1 over root 3, so let's just calculate that then, and we get again pi over 6. But this time we need to consider that theta is going to be pi take away alpha. Okay, so the value of theta is going the whole way around, but stopping alpha degrees short, if you like. So we're going kind of, what's the other side? If we consider that it's on a straight line, they should both add up to 180. What's the other half of that? If one half is pi over 6, what's the other kind of sector of it? So we're going to take it away from pi, so 1 minus 1 over 6, so that gives me that theta is 5 pi over 6. And then I can write down the value for my complex number is 2 cos 5 pi over 6 plus I sine 5 pi over 6. And that's my value for that second complex number there. So maybe we'll look at one more of these examples here. So maybe the minus 2 minus root 2i. So let's just look at that one. So, sorry. So minus 2 minus root 2i is going to end up being down here. Or sorry, not down here, on the other side. So minus 2 minus root 2i is over on the side here. Okay, we're laying it out the same way. This is my value alpha, this is my value for theta, but the difference this time is that theta is going to be negative. So we know it's going to be negative because it's below that real axis. We're working now down in that kind of lower section. We also have to note that when I'm finding the value of theta this time, I'm going to be taking away that alpha from kind of 180 or from pi over 2, the same as we did in the first section. So it's going to be working out kind of not the full value, it's not the same as alpha, but it's going to be taken away from a value of pi. But let's just start it off the same way. We'll start off by finding my modulus. So again, minus 2 squared plus minus root 2 squared. So we get 4 plus 2, which gives me a value of the square root of 6. Okay, perfect. Let's look at the value of alpha. So alpha, again, b over a, and we take it to be positive always. So we're going to be finding tan inverse of, let's see, sorry, let me clear this. So tan inverse of root 2 over 2, and that gives us a value of what? Nice decimal. 0.615. So let's just go that far. 0.615. So that's perfect. Now for this one, we know that theta is going to be negative. So it's going to be negative, and it's going to be pi minus 0.615, and then take the negative value of that, so the negative answer. So we're going to take it away from pi to kind of work out what the other side is, and then we're going to make it negative to get our final answer at the end. So let's just work that out. So into our calculator, we can do pi, take away 0.615, and that gives me a value for theta of minus, make sure we include the minus this time, minus 2.527, and we've cut it off there. So we've worked out again our two answers. The difference there, I suppose, and the particular thing to watch out for is really this part here, working out the value of theta when we have our reference angle, when it's one of those more awkward ones. And the two real awkward ones are in these two sections here. Those are the only two where you need to subtract it in that way. So let's just look then. So that gives me a value for z of root 6 cos minus 2.527 plus I sine minus 2.527. Okay, and that gives us the answer for that one. With a question like that, we're able to have decimals of that form. That's perfectly fine. We may write it in degrees format if you want. Generally, the marking scheme will allow you to have either options, but we tend to use radians when we're working with complex numbers because we're doing kind of this cosine and sine format. And we remember they're kind of periodic functions, and we're going to be looking at something a little bit later as well, which will add into that idea. So it's good for us kind of just to get used to doing it in radians. But that kind of is the general format that we're taking with those ones. We'll look maybe just at the last example rather than, I suppose, leaving one of them. So I'll just take it over to the side here. So if we have part 4, because I'm writing them out a bit big, so it's 1 minus I. So same thing again, we'll lay out where we're going. It's going to be down in this quadrant here, 1 minus I. And again, we can lay out our value for alpha. Now for this question, the value of alpha and the value of theta are going to be the same, except theta will be the negative version of it. So let's find my modulus again in the same way. And these are really just about getting the practice of kind of working them out. So or square root of 2, same as before. Tan alpha is 1 over minus 1 over 1, which gives me that alpha is, I'm sorry, we don't include the minus there. So we're just taking it as positive, as we said. Deleting it all. We're just taking it as positive, so we get tan inverse of 1, so let's just compute that for ourselves. Tan inverse of 1 gives me a value of pi over 4. Perfect, tan inverse of 1 being pi over 4. For this one then, we've already stated that theta is going to just be the negative version. So it's just showing us, by making it negative, we're just showing that, yes, you're going pi over 4 degrees, but you're going to go down pi over 4 degrees. You're going back the way, you're going clockwise, kind of the opposite way to normal. Then we can lay out our kind of complex number, square root of 2 cos minus pi over 4 plus I sine minus pi over 4. And that's the value for that complex number there. So we can kind of see with those 4 examples, we've had one kind of in each quadrant. And you really just have to be careful with the quadrant that you're working in, because that's really going to tell you a lot about the value of theta and the value of alpha and the value of all of these things. And it really does depend where we're working. And as we saw there in the last 2, because theta was in the kind of lower section, theta was going to be negative. In the first 2, theta was going to be positive. And it's a good practice, I suppose, for us just to make that little note beside it. When you're drawing in your sketch, draw in alpha, draw in what theta is going to be, and maybe just make a note that it's going to be positive or negative, just so you can kind of be aware for yourself. So that's kind of our general format, I suppose, for converting from rectangular or Cartesian to polar form. That's something that's really, really important that you're really fluent with, because it's something that can come up quite a lot, and it's used even in later questions when we're using formula and stuff in polar form. A lot of the time you will have to convert it for yourself first of all, so it's good just to be used to that. If we're going the opposite way, if we're converting from rectangular form to polar form, or from polar form to rectangular form, excuse me, then all we have to do is compute those values. So we use our calculator. Say we look at these few examples here. It's 2 cos pi over 6 plus I sine pi over 6. We can start off by just computing cos of pi over 6, which gives me root 3 over 2. And I can go back and do sine of pi over 6, which gives me a half. And I can multiply by 2 and I get root 3 plus I. And that is my value there. Same thing goes with the next example. If I was to do cos of minus pi over 3, I get a half. And if I was to do sine of the same value, that gives me minus root 3 over 2. So again, I get 3 over 2 minus 3 root 3 over 2 I. Okay, and the same thing goes. We're just computing these values. We'll just do the last one. Cos of 5 pi over 6 gives me 1 times minus root 3 over 2 plus I. Let me see if we go with this one then as well. Sine plus a half I, and we can multiply that out. Root 3 over 2 plus a half I. Okay, so to convert from polar form to rectangular form is actually fairly simple. You just compute in your calculator. This is why, and it's something that you can accidentally do for these questions. Sometimes it seems like, okay, well, I'll keep going and now I'll type these back into my calculator, but you're just going to end up back where you started. And it is a good way to check that you've done the right thing, is if you compute it in your calculator, do I end up back with the same answer that I started with? It's an easy way for us to just quickly double check our work. I know sometimes in the exam we just don't have time, but just if there's a particular one that you're unsure about, or if you've later parts to a question that you just want to double check for yourself, sometimes it's no harm. So we have a few practice questions here on converting from polar form to rectangular form and rectangular form to polar form. I'm going to look at these exam questions down here. I'm going to leave the practice questions for you to do for yourself. I'm going to focus on just going through these exam ones, I suppose. So looking at this one, first of all, we have that v is equal to 2 minus 2 root 3I. Write v in the form or cos theta plus I sine theta. So we're writing it into polar form. So we start off, same as we've done in those examples, find our sketch, plot where it is. So it's 2 on the real axis minus 2 root 3 on the imaginary axis. So that's going to put it somewhere around here. Okay, again, it's just a general sketch. So this is my complex number v. We can kind of mark in alpha, we can mark in theta. It's going to be the same as alpha, but we also note that it's going to be negative. Let's work out my modulus. So it's going to be 2 squared plus minus 2 root 3 squared. So or is the square root of 4 plus, let me see, 2 root 3. So if we're unsure, let's just make sure we can work that out. Okay, and we get a value of 12. Okay, again, we should be able to do that. I shouldn't be showing myself up. Get that or is 4. Okay, perfect. And then we'll find tan alpha. And again, we take those values as both being positive. Remember, it's b over a. And think again of, we're looking at nearly like a triangle here. If this was alpha, if we consider where we've gone down to root 3, we've gone across 2, tan would be opposite over adjacent. So it's the 2 root 3 over 2. Okay, that gives me tan alpha of root 3. So alpha is going to be tan inverse of root 3, and we can work that out on a calculator, and that's going to give me pi over 3. Okay, as a value for alpha. We know for this question, theta is just the negative value of alpha, so it's going to be minus pi over 3, and then I can write down my value for v is 4 cos minus pi over 3 plus I sine minus pi over 3. And that's our value for our complex number there. So we can see how kind of quick it can be to actually work those out once you get used to them. Now, the only thing I suppose with that question was they did accept your minus pi over 3 as perfect. We might see in the question that they do say that maybe to do theta between 0 and 2 pi. Now, they completely accepted minus pi over 3, but if we wanted to maybe just be particular, or we were wary of the question or something like that, we could work the other way around for this one, and we could take theta as being, instead of saying the minus pi over 3, if we took it all away from 2 pi, so if we said 2 pi, take away my pi over 3, to get a value of, let me see, 6 pi over 3 is a 5 pi over 3, and we could fill in 5 pi over 3 instead. Okay, but I think we just stick with the way that we're doing it. It is the most accepted, and it is kind of the conventional way of doing things. So we'll just stick with the way that we're going, I suppose. Just again, just keeps things simple for us. Let's look at maybe this last exam question here, and then we're just going to look a little bit at multiplying and dividing then. So looking at this example, if z is 4 over 1 plus root 3i, they say verify that z can be written as 1 minus root 3i. So this is just a quick kind of recap of our division, I suppose. So if we're dividing complex numbers, we want to multiply the top and the bottom by the complex conjugate of the bottom part. So let's just again quickly give this a go here. That's going to give me 4 minus 4 root 3 on the top here. It's going to give me 1 minus root 3i, okay, making sure I put in my i's here as well, minus root 3i plus root 3i minus 3i squared, 4 minus 4 root 3 over 1 plus 3 gives me 4 minus 4 root 3 over 4, which can simplify down as 1 minus root 3i as required. Okay, as required from the questions, we've verified that. Now they said plot z on an Argand diagram and write z in polar form. So let's just focus on kind of writing z in polar form, I suppose. If we do a quick little kind of sketch for ourselves, we can kind of be maybe a little bit more accurate with this one. So say we say this is 1, this is 2, this is negative 1 here. We would say this is 1, this is 2, this is 1, this is 2. And let's just plot that down. So 1 minus root 3i is going to put me kind of somewhere around here. Then we're going to be again sketching it out. We're following actually the same steps as we had in the last one. Theta here again is going to be negative. Okay, 1 minus root 3. So let's find my modulus first of all. 1 squared plus root 3 plus minus root 3 squared. So we get 1 plus 3, which is root 4, which is 2. And then tan alpha is, let's see, root 3 over 1, same as before. We get tan inverse of root 3, which is the pi over 3 that we've already had. And the same thing again, then theta this time is going to be the negative value of that. So negative root 3 over negative pi over 3 shows us we're going back the way we're going clockwise. This time we're going the opposite way to the way we normally would go around the plane. Then if we lay down our complex number here, it's 2 cos minus pi over 3 plus I sine minus pi over 3. And that's our kind of complex number laid out for us there. So converting to polar form, really, really important, but one that you actually can pick up fairly quickly, I think, if you just get the practice of it. That idea of alpha, make sure we're taking alpha as being positive, make sure we can work out the value of theta that we're looking for, and that we can fill in those values as accurately as possible. It's definitely one that's worth putting a bit of time into. So let's just look then at multiplying and dividing in polar form. Again, we mightn't do all of these examples. They're giving you some general ideas here for what happens when we multiply and divide in polar form. So if we're multiplying in polar form, say we have two numbers like they have here, where z1 and z2, and we have a different modulus and a different argument, then for z3, if we had another number, say that was another number that we have where we're multiplying the previous two, the modulus of that one will be the previous two moduli multiplied. The argument is where we add the two angles. So to multiply two complex numbers in polar form, we multiply the moduli and we're going to add the angles. Okay, so keeping the letters the same really. For dividing then, we kind of make the expected substitutions. So we divide the moduli and we subtract the angles. So we kind of reverse or do the opposite of what we would do when we're multiplying. So let's just look maybe at one or two of these examples here. So say we do z1 multiplied by z2. Well, what we've said is let's call that z3. So z3 is going to be z1 by z2. The modulus of this one is going to be the modulus of z1 by the modulus of z2, which is 5 by 7, which is 35. And the angle then, my argument, or I can just call it theta 3, is going to be theta 1 plus theta 2. So again, we don't really multiply angles, we tend to kind of add angles. And that's going to be pi over 3 plus pi over 8. Okay, if we wanted to compute that quickly for ourselves, we can type it in using the pi's, or we could just type in the fractions. It doesn't really matter, but we'll maybe use the pi this time. And we can again just use our calculators just to be confident, I suppose. 11 pi over 24. And let's just write this out then. So z3 is 35 cos 11 pi over 24 plus I sine 11 pi over 24 as our value for that one. We'll just look at the division as well, and then I'll leave the last two for you to do for yourselves. z2 divided by z3. Again, let's give it a name. We'll maybe call this one z4, so it's not just the same as the last one. So my modulus is going to be the modulus of z2 divided by the modulus of z3. So the modulus of z2 is 7, the modulus of z3 is 2. And then my angle, my argument, is going to be the argument from z2, take away, obviously not dividing, the argument of z3, which is going to be pi over 8 minus pi over 4, which is minus pi over 8. So 1/8 take away a quarter, which would be 2/8. So we get minus pi over 8. And we can write down then that z4 is 7 over 2 cos minus pi over 8 plus I sine minus pi over 8. And that's our kind of answer for that one. So these are kind of the main parts, I suppose, of polar form. I know this video is kind of going on a bit, but making sure you're happy with how can I convert from rectangular form to polar form, how can I convert from polar form to rectangular form, and can I multiply and divide when I have them written in polar form? And then just going over those few exam questions that you have in your booklet, just so we can have some worked solutions, I suppose, for those ones. There's a few practice questions there, obviously, that I've left for you to do in your own time, and you have the solutions for those as well. So we're going to look next at some of the theorems, a particular theorem that involves these polar forms and looks at kind of computing powers specifically of these polar forms.